In this video, I'm going to talk a bit about molecular geometry. And so this is predicted using what's called valence shell electron pair repulsion theory, which is shortened to VSEPR, and that's usually pronounced VSEPR, even though it's VSEPR, and that's probably just because it rolls off the tongue better than VSEPR theory. But VSEPR theory just says that bonds and lone pairs are groups of electrons around the atom, and electrons are all negatively charged, and objects with the same charge will repel each other. Therefore, the electron groups around an atom are going to repel each other. The result is that the electron groups, the lone pairs and bonds, around an atom are going to move as far away from each other as possible. And this is observed in the three-dimensional structure of molecules. So for instance, the fact that carbon dioxide looks like this, it has 180 degrees because that's as far away from each other as possible that those two electron groups can get. But if we have something like water that looks like this, we can put kind of a line there where one of the lone pairs is, and what you would find is that the bond angles between each of these things is 109.5 degrees. And we'll see what the consequence of that is here in a little bit. So we're talking about molecular geometry because molecules have a three-dimensional structure, and the shape is based on how the electron groups are oriented around the central atom. And as we saw, the way they will orient themselves is based on this VSEPR theory. And so the electron groups that we're talking about consist of lone pairs. So one lone pair is one electron group, and bonds, where a single, double, or triple bond all count as one electron group. So if we have things that look like this one on the left would have 4 electron groups, and so would the one on the right. And we can show the 3D structure using these wedged bonds and dashed bonds, where wedges are coming out of the screen and dashes are going into the screen. So that means that these wedges right here are sort of pointing out of the screen, and these dashed bonds here are pointing into the screen. And so we can differentiate between what's called electron group geometry, which is the geometry that includes all of the electron groups, and what's called the molecular geometry, which is the geometry that includes only the bonding electron groups. So for instance, this one has a bond there, where this one has a lone pair there, and so the one on the left is going to have an electron group geometry that's called tetrahedral, and this molecular group geometry is also going to be called tetrahedral, where this one here has an electron group geometry of tetrahedral because we see they both have 4 electron groups. But then the one on the right will have a different molecular geometry because one of its electron groups is a lone pair. And so its molecular group geometry is what's called trigonal pyramidal, or trigonal pyramid, or sometimes just shortened to trig pyramid. And so we can think about these groups this way. If we have something that has 2 electron groups and no lone pairs, then its electron group geometry is going to be linear, and its molecular group geometry will also be linear. If we have something that has 3 electron groups and 0 lone pairs, then its electron group geometry is going to be what's called trigonal planar, and its molecular group geometry is also going to be called trigonal planar. And then if we have 3 electron groups, but one of them is a lone pair, again, its electron group geometry is trigonal planar, but its molecular geometry will be called bent. Then if we have something with 4 electron groups and 0 lone pairs, then the electron group geometry is tetrahedral, and the molecular group geometry is tetrahedral. If it has 4 electron groups and 1 lone pair, then the electron group geometry is tetrahedral. Molecular geometry is trigonal pyramid. Then if we have 4 electron groups and 2 of them are lone pairs, then the electron group geometry is tetrahedral, and the molecular geometry is called bent. And so these shapes we're talking about look kind of like this, where linear just means that we have 2 electron groups and they are exactly 180 degrees away from each other. If we have trigonal planar, what that means is that it makes a triangle and it's all in the same plane. So it's just a 2-dimensional triangle, and the electron groups are going to have 120 degrees of separation from each other. Tetrahedral looks more like this, where we have a central atom here. We have the 4 electron groups, and they're going to orient from each other 109.5 degrees. And so we can think of it looking like this. So they call it tetrahedral because the terminal atoms make a tetrahedron shape. So this is a tetrahedron right here, and we see that the terminal atoms around this make a tetrahedron shape. So we call it tetrahedral, and there is going to be 109.5 degrees of separation between each of those terminal atoms, each of those electron groups. And so we can look at a few examples here. So for instance, two electron groups in 0 lone pairs. That's our carbon dioxide there. It has just 2 bonding groups and no lone pairs, and so it has an electron geometry of linear, molecular geometry of linear. Then if we have 3 electron groups in 0 lone pairs, that would be something like our sulfur trioxide here. So the electron group geometry is trigonal planar, molecular geometry trigonal planar. Then if we have 3 electron groups in 1 lone pair, that would look like our sulfur dioxide here. So again, the electron group is trigonal planar and molecular geometry is bent. Then if we have 4 electron groups in the 0 lone pairs, that would be something like our methane here. So again, electron geometry tetrahedral, molecular geometry tetrahedral. If we have 4 electron groups in 1 lone pair, that would look like our ammonia here. So again, electron group geometry tetrahedral, molecular geometry trigonal planar. Then if we have 4 electron groups in 2 lone pairs, that would look like our water here. So again, electron group geometry tetrahedral, molecular geometry is bent. And so some things to notice here is that if the number of electron groups and the number of bonding groups are the same, then the electron group geometry and the molecular geometry are the same. So we can see that across this top row here, where if we have 0 lone pairs, then the electron group geometry and the molecular geometry are all the same. And the electron group geometry does not change if the number of electron groups does not change. So that means that the electron group geometry is the same within a column of our table. So we see in the 2 electron group geometry, there's really only 1 spot, so it doesn't really apply much there. But then with the 3 electron group geometry, we see that no matter how many lone pairs we have, the electron group geometry is trigonal planar. With 4 electron groups, no matter how many lone pairs we have, the electron group geometry is tetrahedral. Then we also see that the molecular geometry can be called bent, whether it has 4 electron groups and 2 bonding groups, or if it has 3 electron groups and 2 bonding groups. So we see bent showing up in both of these ones here. And lastly, there are no geometries given for the 2 electron groups and 1 or 2 lone pairs, or for the 3 electron groups and 2 lone pairs. In any of these cases, it would just either be the case that we have a single atom or just 2 atoms bound together, and neither of these are designated a geometry, so that's why these spaces here were left blank. And so now we can go through a few examples here of trying to predict the geometry for these. For each one of these, I would encourage you to pause the video and try it on your own. So draw the Lewis structure, then try to determine what the geometry is, just based on the number of electron groups and the number of bonding groups for it. So for the first one, we have silicon tetrachloride. If we want to make the Lewis structure for it, we would draw it like this. Then we want to count up the number of electron groups. There are 4 of them, and the number of bonding groups. There are 4 of those, so we have 4 electron groups, 4 bonding groups. That tells us that the Eg is tetrahedral and the Mg is also tetrahedral because the number of electron groups and the number of bonding groups are the same. So if we drew this in 3 dimensions, we would want to use the wedged and dashed bonds, and so make it look like this. Each of the bonds should be 109.5 degrees from each other. The next one, we have HCN, so this is hydrocyanic acid. We want to first come up with the Lewis structure. That would look like this. We want to count the number of electron groups. There are 2 of them. Count the number of bonding groups. There are 2 of those, and so that means that this would be linear for both the Eg and the Mg. And this is what our 3-dimensional structure would look like. So there really isn't any change for this one. The next one, we want to come up with the geometry for HPO. So we first want to come up with the Lewis structure for it. That would look like this. We want to count the number of electron groups. There are 3 of them. The number of bonding groups, there are 2 of them. So now we have a different number of bonding groups than electron groups. There are 3 electron groups, which tells us that the electron group geometry would be trigonal planar, and 2 bonding groups, which would tell us that it is bent. So this is what the 3-dimensional structure would look like. Remember, trigonal planar just means that is a triangle in the same plane, so it's just a two-dimensional triangle, so we don't have to draw any of our wedges or dashes for it. The next one, we have sulfate, so we want to come up with the Lewis structure for this, so that would just be this. Then we want to count the number of electron groups around the central atom, so there are 4 of those. Then the number of bonding groups around the central atom, there are 4 of those. And so that means we have a tetrahedral electron group geometry and a tetrahedral molecular geometry. And this is what it would look like with the 3D structure. The next one, we have phosphorus trichloride. So again, the first thing we want to do, we want to come up with our Lewis structure that looks like this. Then we want to count the number of electron groups. There are 4 of them. Then the number of bonding groups. There are 3 of them, so 4 electron groups, tetrahedral. Then with 3 bonding groups on a 4 electron group molecule, that's going to be trigonal pyramid. So electron group geometry, tetrahedral, molecular geometry, trigonal pyramid. And so this is what it would look like in 3 dimensions. The next one, we have boron trifluoride. We want to come up with the Lewis structure for it. So that would look like this. We want to count the number of electron groups. There are 3 of them. The number of bonding groups, there are 3 of them, and so that means this would be trigonal planar for both the electron group geometry and molecular geometry. And this is what it would look like for the 3D structure. Again, this is just a trigonal planar, so it's just a 2-dimensional triangle for the structure for it. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.